Hello, my name is Nikitaev, and I'm a PhD student at the University of Alabama in Huntsville, and today I'll be presenting my research on seeded hydrogen propellant in nuclear thermal propulsion engines. My advisor is Dr. Dale Thomas. So what is nuclear thermal propulsion? This is an engine that does not depend on chemical combustion to produce heat. Instead, it relies on a nuclear reactor to produce heat by nuclear fission. These engines were tested and well documented by Project Rover and the NERVA program, and they are currently under consideration by NASA as a viable propulsion system for a crewed mission to Mars. Currently, Aerojet Rocketdyne is working on such an engine, and we can see the power balance model here. UAH has a Simulink model of this engine, and it is within 1% accurate of Aerojet Rocketdyne's values. So what's wrong with pure hydrogen propellant? It is lightweight, which means you're going to have low vehicle mass. It has low molecular weight, which means that the engine will produce thrust at high specific impulse. The cons of this propellant is that it has low density, which means your vehicle is going to have large propellant tanks, high specific heat capacity, which, although is great for removing reactor heat, it is not so great when we want to heat up this propellant. It also has a low boiling temperature of 20 Kelvin, which could mean that we're going to need active cryocoolers. This is an area of research. High viscosity, which means we're going to have some high duct pressure drops, and this is due to the fact that the propellant has low density, which means we're going to have high volumetric flow rate through those ducts. So why are we considering seeding hydrogen first of all? Well, seeding is a process of adding an impurity to a base fluid to alter the thermophysical and transport properties. Synthetic car oil is seeded with solid nanoparticles of metals, which enable it to more effectively take out the heat from the car engine. But solid particles will congest the fuel element channel of the NTP engine, and we're also not considering molecules with high hydrogen content such as methane and ammonia because we're going to need to be breaking those bonds by thermal dissociation. And why are we doing it with heavy noble gases? Well, they are non-reactive. They have very low specific heat capacity, and most are very dense. The noble gas of interest in this study is argon due to its easy accessibility and low cost. So here we can see how the seeded hydrogen properties change with the argon molar concentration. We can see that the density increases, the specific heat capacity decreases, while the viscosity and thermal conductivity increase and decrease respectively at a much lower rates than the density and specific heat capacities. And these two are the properties that we are most interested in for our pressure losses and convective heat transfer. In order to seed the hydrogen, we need to add some hardware such as a turbine circuit to power the seed pumps. And this seed is going to need to get some of its heat by cooling the external of the nuclear reactor. And then it will be mixed inside a T-valve, and because these two fluids are at supercritical phases, supercritical fluids are completely miscible with each other, so we don't need any kind of mechanism other than the said T-valve. So the convective heat transfer increases, and we can see this with the delta T between the channel surface temperature marked in green and the bulk propellant temperature marked in blue. This difference is seen to decrease here at the maximum seed, such as 6% molar of argon, while the maximum fuel temperature remains constant. We also observe that the outlet temperature from the reactor is increased slightly. However, we do require an increased reactor propellant pressure, but this is more than made up by the decreased pressure drops throughout the turbomachinery and ducting due to the higher density of the propellant. The engine performance is shown here, where the thrust is relatively constant, but the reactor power decreased quite a bit, in fact, all the way down to about 77%. However, the specific impulse also decreases, as shown in blue, along with the reactor power, shown in red, and due to this, the vehicle mass will be higher. The vehicle performance, however, is increased, as shown here by the delta V, with the gray area being the expected vehicle performance, as indicated by the design space. And this increased delta V can be translated to reduced travel time up to 10%. It can also be used to widen the thrust band during reactor transient events. So as the reactor heats up, we can start seeding in this area, and we can get a wider band of the same thrust as shown here, whereas with the case without the seed, we see that the maximum thrust actually follows the reactor curve. So today we have discussed seed as a new degree of freedom for NTP engines. We can tune the required reactor power without compromising thrust. We can decrease the travel time by up to 10% without increasing the volume, and we can produce the same thrust longer during reactor transient events. Future research will include decreasing the vehicle volume with the same delta V, and also launch vehicle consideration due to the increased mass of the vehicle. Thank you very much.